These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. What is the first framework that we've covered in this course?
Kinetics and projectile motion.
Say that again?
Kinetics.
Good. The term that we use is kinematics. Kinematics.
Kinetics.
And projectile motion. Good. Now, remember that to begin with that section, that there's really two different approaches to kinematics. You have to identify whether it's a problem where the acceleration is 0, or a situation where the acceleration is not 0, and then deal with one of those two cases. Okay? What was our next framework?
Is Newton's second law, or applying Newton's second law.
Okay, well, what's the key equation that we write down to organize our work for Newton's second law?
We have two different components where the first one's the sum of force Fx equals dx, and then same thing with y, sum of Fy equals ma.
Good, that's a good way to describe it. So since this is such a key equation, we want to write it exactly correctly, and this is the best way to write out that equation. That's good. And what's the third framework in the course?
Conservation of energy.
Right. Okay. So we know, so I'll tell you right off the bat, what's the framework that we apply to circular motion problems? Or maybe you tell me, have you picked up from class which of these frameworks do we apply to circular motion problems?
Newton's second law.
Newton's second law, which is one reason why we've been working so hard on that framework. Well, we've seen that one of the keys to using Newton's second law is to write down your axes. Usually we have a horizontal and a vertical axis. What do we usually call this axis?
X.
And this one?
Y.
Those are just arbitrary names. If you wanted to, you could call this W and this Z, or this one Bob and this one Alice. They're just names. You can call them anything you want. X and Y are just the conventional names. Now, we've seen that you can't get too attached to the horizontal and vertical axes, because on some problems you might have different looking axes, say on an inclined plane problem, like this. We were still using the same names as before, X and Y, but again, we could have used any names for those two axes. Well, when you're doing a circular motion problem, one thing to keep in mind is actually in reality there's always three axes, right? X, Y, and what we could call Z, right? Isn't there also another axis that's hard for me to draw, but that's oriented like my pen here, going into and out of the board? There's also an axis here that's going into and out of the board that we might commonly call Z. So there's really three axes, although in most problems we only need to really focus on two of the axes. So now moving on to circular motion problems, again there's going to be three axes, but we have some new names for these three axes. We can keep using X, Y, and Z, but we need other names in addition to that. One of our new names is going to be the radial axis. Another name is going to be the tangential axis, and the third axis doesn't have a cool name. All right, so the three axes now, instead of being called X, Y, and Z, they can be called radial, tangential, and one that doesn't really have a special name. So let's look here at point A, that's at the bottom of this circle. Now, you always want to draw one axis that's pointing towards the center of the circle. And you always want to draw one axis that's in the direction of motion. So let's say here that we are moving clockwise. the object is moving clockwise, what's the direction of motion at this point? To the left. So I should draw one of the axes to the left, which might not be your normal inclination, but you want to draw one axis in the direction of motion and one axis that's towards the center of the circle. Now, in the past, we would generally call this the x-axis and this the y-axis. And that's fine, we can keep calling them that, but we also need new names. I haven't really explained the terms yet, but which of these do you think is the radial axis?
X-axis.
Let's say Y.
Oh no, the Y, sorry.
Why is this called radial?
What are the things?
Isn't it pointing along the radius of the circle? Right? If I put the axes right here, the y-axis would be pointing along the radius. So this is what's called also the radial axis. It's actually a pretty logical name. Here's our radial axis. And what's the name of the x-axis?
Tangential.
Do you see why that name makes sense? Wouldn't this axis here be tangent skimming along the circle? So now we can call these also the radial and the tangential axes. Now, of course, there's also a third axis, the z-axis, that's going into and out of the page, and that doesn't have any special name. Okay. Well, I just did an example for you here, so now's your turn, part B. Try to draw the appropriate axes at this point and give them appropriate labels, just like we did over here. Okay, good. So the important thing is that we want one axis pointing towards the center of the circle along the radius, which is radial, and you both drew this axis down. We don't normally draw the y-axis down, but that would be the direction of motion if we're moving clockwise. Maybe I should remind us of that by just putting this in. So that would be our tangential axis. And if you want, you can keep calling them x and y. But here's something interesting. Which was the radial axis here, x or y?
X.
Which was the radial axis here?
Y.
Okay, so you can see how you name the axes depends where you are on the circle. How you name the axes depends where you are on the circle. You can't just say x is always radial or y is always radial. Okay, looks like you both got that right, so let's also do point C here. In fact, I think you're getting the hang of it, so when you're done with that, go on to point D. Okay. How do you decide whether this should be pointing left or right?
This one? Because of moving clockwise. It's
You're right. Good. So here's tangential, and here's the radial axis, since we're moving in this direction. So notice that at this point, the tangential axis would be best drawn as up. But at this point, the tangential axis would be best drawn as down, because your direction of motion changes when you're moving in a circle. Okay, so that's how we would draw our axes. Again, we might call this also the y and this the x. Again, there's also a z-axis that doesn't have a special name, and it probably wouldn't be too important for a vertical circle like this. Okay, I'll also tell you right off the bat, which axis is usually going to be the, so how are we going to use this? Well, remember we're plugging this into Newton's second law. So we have one version of Newton's second law for the x and one for the y. But instead of calling them x and y, what could we call them now?
radial.
Radial and tangential. We have one version of Newton's second law for our radial axis and one for the tangential axis. However, on most of the problems that you're going to see in this course, you're really only going to need one. You're only going to need Newton's second law for one of the axes. Which axis do you think is going to be most useful for solving circular motion problems?
The X.
Now, x and y don't mean very much to us for a circle, right? Remember, we want to use radial and tangential.
Radial.
Turns out that the radial, in fact, maybe just about all the problems you'll see in the introductory course, the tangential axis may never even come up. You're going to probably be able to solve all the problems in this course just by doing Newton's second law for the radial axis. So what have we added that's new? We haven't added much that's new except some new names for our axes here. The only other thing we have that's new is that we're going to have one new formula. There's a formula for calculating the magnitude of the radial acceleration.
V squared over radius.
That's right. So this is one new piece that we have now for circular motion. When something is moving in a circle, we have, this is the radial acceleration. What does this variable on top stand for? And this one? Oh, the circle that we're talking about. Maybe we should talk about why that makes sense. So let's review a little math. If I increase y and I hold z constant, what would happen to x in this equation?
It'd get bigger.
If I increase z and I hold y constant, what would happen to x in this equation?
It's smaller.
Because z is on the bottom of the fraction. So this is an equation that says y and x move in the same direction and x and z move in opposite directions. So think about, say, if you're driving down the road and you have to drive around a curve like this. When will it be more difficult to drive around the curve? If you're driving fast or slow?
Fast.
You know this from driving, right? It's dangerous to try to take a curve when you're driving too fast. That's why there's usually a sign saying to slow down. The faster you're going, the harder the curve is. So, if your speed increases, does that make it easier or harder to take the curve?
Harder.
Harder. Is it harder because you have to accelerate more or less to take the curve?
Accelerate less.
Now the acceleration is what you have to do to actually move around the curve.
Yes. Yeah.
So would this mean you have a higher or lower acceleration?
Higher.
Higher. You have to accelerate more to take the curve. Maybe we don't have quite enough time to go into all the details here, but remember, the acceleration tells you how your velocity is changing. But remember, velocity is not the same thing as speed. What's the difference between them? What does the velocity tell you besides your speed?
Direction.
Direction. So this is not an acceleration that's changing your speed. You don't have to change your speed to move around the curve. This is the acceleration that's changing your direction of motion. So the point is that the faster you're moving, the faster you're going to have to change your direction of motion. So the more acceleration you're going to need. So we're not using acceleration as it's used in ordinary English. We're not saying you have to accelerate a lot to change your speed here. We're saying you have to accelerate a lot to change your direction. If you were going very slowly, you would have lots of time to change your direction, so you wouldn't need as much of an acceleration. So do these two variables move in the same or opposite directions?
Same.
That's why v is on the top of this fraction.
Makes sense.
Okay, now here's two different turns that you might make. Does this turn have a bigger or a smaller, does this turn have a bigger or a smaller r?
Smaller.
This one has the smaller r. Smaller r. Does that make it a harder or an easier turn?
Harder.
You know, again, from common sense, this turn is much easier to take. Here, this turn is going to be this is a sharper turn. This is going to be much more difficult to take. So a smaller r means a harder turn. Is that because you have to accelerate more or less for this harder turn?
Accelerate more.
Right. Remember, again, this is not an acceleration that's going to change your speed. It's an acceleration that's going to change your direction. Because you're making the turn over a very short distance, you have to accelerate quite quickly to accomplish that turn. This, again, is why the sharper the turn, the more you have to reduce your speed in order to be able to take that turn. So r and a, do they move in the same or opposite directions?
Opposite.
That's why r is on the bottom of the fraction. So we're not going to prove this equation, but you should know that the equation makes good sense. The equation is saying that the faster you're going, the harder the turn is to take, and the smaller the radius, the harder the turn is, because a smaller radius really means a sharper turn. A smaller radius, as you can see in this picture, means a sharper turn, which is more difficult. You need to accelerate more to change your direction. Remember again, does the radial acceleration change your speed or your direction? We were just talking about how this acceleration is the acceleration that's going to change your direction. What's happening to the object's speed? Well, we can't tell. Sometimes you can speed up when you're taking a curve, sometimes you can slow down, or sometimes you can take a curve at constant speed. The radial acceleration tells you how your direction is changing. That's not how we use acceleration in ordinary English, but it's how it's used in physics. The acceleration can tell you how speed or direction is changing. Well, the radial acceleration tells you how your direction is changing. By the way, it turns out that the tangential acceleration tells you how your speed is changing. Tangential acceleration tells you how your speed is changing, but we're not going to really have to get into that much, because remember we said we're really not going to need tangential acceleration much for solving problems. So could I say that AT equals v squared over r? Can I say that tangential acceleration equals v squared over r?
No.
No, this only applies to radial acceleration. That's the whole reason why we're going to focus on the radial axis, because we have a special formula for it. Do we have a special formula for tangential acceleration? No. Do we have a special formula for radial acceleration? That's why we're focusing on the radial axis. Okay. So let's imagine now a box that is sliding clockwise around this track. A box that's sliding clockwise around the track. And let's say that at this point we have a speed of 20 meters per second. Let's say, well, let's not bother. Okay. So let's try to, and let's say that this has a radius of 10 meters. And let's start trying to figure stuff out. So let's go through this together. What framework are we going to use?
We're going to use the Newton's second law.
So one thing we need is axes. Well, I think we already talked about what good axes would be at this point. Here's our radial and tangential axes. Now we need our free body diagram. So what's one of the forces on this object?
The weight.
We always start with the weight. And what direction is that in? The weight down. All right, and what's another force on this object?
That's it. We don't know how it's moving, do we?
Well, it's the same situation as before, where we're moving clockwise, although that's not really too important for finding the forces. So anything else we can do here to identify more forces?
No.
So you're saying there's no other forces?
Yeah.
Oh, so again, this is a 5 kilogram object moving around a track.
Acceleration?
Is acceleration a force?
No.
Okay, what are the units for acceleration?
Meters per second squared.
What are the units for force?
Yeah.
Newtons. Well, let's go over this two-step process that we've talked about for identifying all the forces. Step 1, identify the weight. And then what's step 2?
Whatever's touching the
Contact.
Is there anything touching this object?
No.
No?
Oh, okay. There's a track. It's a normal force on the track.
Right.
Yeah. So maybe I didn't quite specify this clearly, but it's not just going to be hovering in the air, right? So this represents some kind of wooden or metal track that we're moving around. So what's touching this object?
The floor.
Track.
The track, yes. So what would be a force that could exert?
Force.
There could be friction, good,
Normal force.
and normal force. What would be the direction of the normal force?
Going straight up.
How do you know?
Because it's
How do you figure out what the direction of a normal force is? The normal force always points away from the surface. The normal force always points away from the surface, and the surface here is the track. How do we figure out the direction of the normal force? The normal force always points away from the surface. Well, at this point, the direction that's directly away from the surface would be straight up. And if there were friction, what direction would that be in?
To the right.
Because we said we were moving clockwise. It's also possible it might be a frictionless track, but if there were friction, the friction would be in this direction. Okay, no other forces because there's nothing else touching the object. So that's a very important two-step process that we talked about yesterday. First, identify the weight, and then what's the other step?
Against contact.
What is touching the object? What is touching the object? Okay. Okay, so then we make our force table. So we can start with the weight. What can we write down about that?
W equals mg.
Good. So what does that give us?
W equals 5 kilograms times 9.8 meters per second squared.
So 49 newtons.
Okay. So go ahead and what would be W? And maybe instead of using X and Y, we could use radial and tangential. So what would be W radial?
Quick question, would it be negative?
You tell me.
I think it would be right.
How do you know?
Because the radius, the axis is pointing upwards and we're in the opposite direction.
That's why we had to choose our axes. So that's good that you were thinking about that. Our radial direction here is up, but we know the weight is down. So what should I write for W radial?
It's going to be negative.
Negative what?
49.
Okay. And how about W tangential?
0.
Okay, good. Okay, that's good that you were thinking about the sign and you got the correct sign. That's why you did that exercise on finding the axes. We need the axes so we can get the correct signs. Okay, so how about the normal force? What can we write down about that?
Magnitude of normal force.
What can we say about N radial and N tangential?
N of x is equal to, oh, sorry, we're negative x. Negative r is equal to positive magnitude of n. And n of y equals 0.
Or N tangential is 0. Good.
I gotta get that on my.
You could use X and Y if you wanted, if they were labeled as the radial and tangential here. Okay. Then we have the frictional force. What could we write down about its components?
Mu k times magnitude.
Times n.
And we know mu k here is, did I tell you mu k? Oh no, I didn't tell you, so we wouldn't know that. But what could we write down about the components?
Frictional kinetic force of x is
Radial is 0.
0. No, it's not 0. It is negative. Is it?
What's this 0?
Oh, it's 0 because tangential is
So what's this?
0.
0.
And what's this?
Negative mu k n.
Okay. So notice how we're trying to tie this new material into the force table that we went over before. Okay. But we have to be very careful to think through each step until we start to get more comfortable with this, using our new axes. So notice not everything is radial. The frictional force here is not radial, which means that we probably don't care very much about it. Okay, so now we've dealt with all of our forces. So we're now going to deal with Newton's second law. Well, which version of Newton's second law might be helpful here?
The first one.
The
Radial or tangential?
It's radial.
Yeah, usually in these problems you only need the radial component, usually. So I write F radial equals MA radial. And what do we list on the left-hand side?
We're going to have negative 49 newtons plus
n
n dot
plus 0 is equal to n.
plus 0,
It's equal to
5 kilograms
then
times
a radial.
What do we plug in for A radial?
A radial.
a radial.
Hmm.
A radial.
Oh, yeah. What do we plug in for A radial?
We have to solve for.
Anything we can plug in for this?
We can play
Yeah. So when we were doing problems before, I kept trying to trick you into plugging something in for A when you couldn't. But here you really can plug something in for A. So what do I plug in for A? V squared over R. You you may as well just plug that straight into the equation here. You can just go ahead and plug that straight into our equation. That was the whole reason why the radial version of Newton's second law is more helpful than the tangential, because we have that special equation. Can we plug anything in for V?
No.
Yeah, we have 20 meters per second.
So the problem here said we were moving at 20 meters. Don't forget to square that. And how about R?
10.
Okay. What can we do now?
We can solve for n dot.
Now we only have one variable left, so we can figure something out. Okay.
249.
Algebra wrong. Okay, 10, 200.
So let's talk about this for a second. So I think this is one of the equations that you got. Does this match your paper?
Yeah.
Yes.
Okay. Now I'd like you to tell me what is the next algebraic step that we need to do for solving this equation.
Add by 49 instead of dividing by 49.
There you go. How do you know to add instead of dividing?
That's a negative sign and...
So remember the rule for algebra is how do you get rid of something? By doing the opposite. Well, this is being subtracted from the left side, so we get rid of that by adding. All these little steps are crucial to get through the entire problem.
249. Alright.
So what's the normal force?
Positive 249 newtons.
Okay, so we figured something out. So that might be something that might be helpful for answering the question here. We figured out what the normal force is. Notice, was the normal force equal to the weight?
No.
No. Even though they were the only radial forces. Even though there's only two radial forces, the weight still doesn't, the normal force still doesn't balance the weight here. Because in this case, the normal force has to be strong enough not only to balance the weight, but also to change the object's direction and move it in a circle. So to actually move us in a circle, the normal force has to be much greater than the weight. So what is this normal force doing? It's changing the object's direction so that we can move in a circle. Remember, what do radial forces do? They change the object's direction. What do tangential forces do? They change the object's speed. We don't have to worry about that so much for this, but clearly that's true, right? The friction would be slowing this object down if there were any friction. It's the radial forces that change the object's direction. Okay. Okay, well this is a good example of how to attack something using circular motion. You can see it's just an extension of what we talked about before. So the key thing is we have to choose our correct axes. We have to be very careful to get the exact right force table, as usual. This turned out not to play any role in our solution, but we don't know that until we kind of worked it out, so it's still best to work it out here. You could now go ahead and also do the tangential component. You could actually figure, sometimes you can figure something out for the tangential component, but that's rarely tested, so we won't go over that because you're rarely going to need that on exams. We'll focus on what you're probably going to need on exams, which is the radial component. Okay, so that's our example. All right, so when do we use this equation for a circular motion problem? What types of circular motion problems are you going to use this equation? Well, a trick question, in your course, you're probably going to use this on 100% of circular motion problems. Pretty much every single circular motion problem you see, guaranteed, pretty much you're going to need this equation. Where do you plug it in? Right here. It would be easy to forget that because we've never used that before, but every circular motion problem, you're going to need to plug that in here. There's no version of this for tangential, which is why we're not focusing on the tangential component as much. Okay, good. All right, so that would be important to go back and try again. You have that in your notes? Can I erase this?
Yeah.
Yes.
then let's move on to point D. And let's figure out stuff about that. Now, first of all, logically speaking, would you forget about physics and think about common sense. Remember that at this point, the object was going at 20 meters per second. By the time it gets to here, based on common sense, would it be going faster or slower than 20 meters per second?
Going faster. No, slower.
Which one?
Slower.
Isn't that just common sense? First of all, you know gravity is going to slow it down. As something moves up a hill, common sense tells you it slows down. And if there were friction, it would slow down even more. Okay, so without ever taking a physics course, we would know this number should probably be smaller. You can't calculate what it is, but I'll just make up something, and let's say that at this point, let's say that our speed is 15 meters per second. Okay, so we've already written down our axes. So we have to identify all the forces. What would be one of the forces on this object?
Weight.
The weight. We always start with the weight. What would be the direction of the weight?
To the
Left.
So you're saying the weight is in this direction?
weight.
No, it's going straight down.
Yeah,
So what's the direction of the weight?
straight down.
Straight down.
Yeah. What is always the direction of the weight?
Straight down.
The weight is always straight down. Again, you just know that from common sense. Earth's gravity never yanks you to the left or yanks you to the right. Earth's gravity is always pulling you down to the ground. Why did you guys say left or right? Well, your thinking might have been contaminated by some of the other concepts on this problem. Remember, we have to think about each force separately. The weight is always straight down. So, here the weight would be in this direction. Are there any other forces on the object?
No.
Normal force. What direction would the normal force be in?
To the right. Perpendicular.
Excellent. That is the right answer. I don't think we've ever seen a normal force that's to the right. How did you know it would be to the right?
Because it's going away from the surface.
That's right. That's why we were reviewing that earlier. The normal force is always away from the surface. Well, in this case, the surface, I haven't drawn the box, but the surface is to the left of the box. So the normal force would be pointing in this direction. So we can't get lazy and think that normal force is always up. That's just for simpler problems. So here's the normal force and the other possible forces.
Friction.
If there were friction, then there could be friction. And what direction would that be in?
Down.
Going down.
Same direction.
Because it's still moving clockwise,
Yeah.
and it's going to oppose motion. So we could have if there were friction, which I haven't given you enough information to tell, but if there were friction, it would be down. Any other forces?
That's it.
Because there's nothing else touching the object. Okay. Good. So now we have our force table. So what's W dot?
Equals mg.
And what would that be?
W equals. Do we have a weight for that?
5
Or is
It's
it
still the same
same
box.
thing?
Same thing, so
I keep forgetting
49.
circular motion.
Negative 49 units.
Now the magnitude, we won't put in the negative sign yet, but its magnitude is 49 newtons. What would be Wx and Wy?
Wx would be 0.
Oh, let's
Wy.
stick with radial and tangential.
I got lost right now.
W radial would be
0
and tangential?
would be negative 49. And it's
Okay, good. We wouldn't get that right if we had thought that the weight was to the right or to the left. We have to get the directions of the forces correctly so we can get the force table correct. Then we have a normal force. So what can we say about normal radial and normal tangential?
So normal radial is going to be positive
and
dot, and normal
and
tangential is going to be 0.
yeah.
Good. And then we have the frictional force. So that's still going to be mu k times n dot. So what would be Fk radial and Fk tangential?
K radial is 0.
And K tangential.
Fk
It's a negative mu k.
times n dot.
Okay. Good. Okay, so what component do we usually focus on?
The radial component.
Good. So for our radial component, we have sum of the forces radial equals ma radial. What would we write down on the left-hand side?
Left-hand side is going to be 0 plus n dot plus 0
And how about over here?
equals 5 times v squared over r.
Yeah, we can't forget to plug in a radial, v squared over r. And v would be,
15.
I just made up a number here, 15. And r would be,
10.
10.
the circle hasn't changed, so r is still 10.
Be 112
5
newtons.
Okay, and you could go ahead and now do the tangential equation, but that probably usually won't be important on tests, so we'll just stop with this. Okay, let's try to compare this to our earlier example. What were the radial forces at point A? What were the radial forces at point A?
Friction. Oh, sorry.
No, it's
I mean
weight
weight and
No,
weight
it's
and normal force.
Weight and
Oh, so it is weight and newtons. Normal force.
weight and the normal force. We might say the weight here is anti-radial, since it's pointing away, but the weight and the normal force. What are the radial forces at point D?
It's gonna be
Just the normal.
normal force.
So our analysis was quite different,
Yeah.
wasn't it? This was the key thing that was different. The weight played a completely different role. At point A, the weight went into this equation. If you look at your notes, we used the weight of this equation. But at point D, the weight was not in the radial equation. And you can only do that by painstakingly making your free body diagram and your force table to decide who's going to be in the equation, who isn't. So the weight played very different roles at this point and at this point. What is it that's making the object move in a circle here?
The normal force.
Yeah, it's the radial forces that turn you to move in a circle. The radial forces are the things that keep you moving in a circle. So here's the normal force that's keeping us moving in a circle. And what were the forces? There has to be some radial force to keep you moving in a circle. And what were the forces that were keeping us moving in a circle here?
Weight and normal force.
Yeah, although actually the weight is trying to break us out of the circle, isn't it?
Yeah.
The weight is trying to break us out of the circle. It was the normal force that was keeping us in. I think this normal force is much smaller than in the first part. What was the first normal force we got?
249.
Why is this? So notice it's much easier to stay in the circle here because the weight's not fighting against you anymore. And also because you're going slower. Remember, it's easier to make a slower turn than a faster turn. So we could have predicted this normal force would be smaller than here. Okay? There's two different types of ways that we classify forces in this course. There are types of forces, and there are directions of forces. For example, if I say something is a weight force, have I told you the type or direction?
The type.
Yeah, of course you can figure out the direction from that, but weight is a type of force. How about normal force? Is that a type or direction?
Type.
How about frictional force? Type or direction?
Type.
Good. How about spring force? Type or direction?
Type.
We haven't talked about that yet, but you might have seen that in your course. How about X force? Type or direction?
Direction.
How about Y force? Type or direction?
Direction.
So if we say Fx, that's a direction. And if we say Fy, that's a direction. How about radial? Is that a type or a direction?
Type. Direction. Or radial.
Looks like there's some disagreement. Is it a type or a direction? It's a direction. But that's one of the biggest sources of confusion. A lot of people think that radial force is a type of force. They say, oh, what's keeping it moving in the circle? The radial force. Well, that's meaningless. That doesn't tell you anything. That's not a type of force. How about tangential? Is that a type of force or a direction?
Direction.
Okay. By the way, let me introduce some new words that we haven't used yet, but your instructor might use. Many instructors don't call this the radial force, the radial axis. They call it the centripetal axis, and you might have heard that in class. I like to avoid that because I find it leads to some confusion. But anyway, which direction is centripetal, radial or tangential?
Radial.
Yeah, so centripetal means the same exact thing as radial. Centripetal means the same exact thing as radial. Centripetal means pointing towards the center, so you can see it is a logical term. Okay, what is a centripetal force? Are centripetal forces a type of force or a direction?
Direction.
But that's what most people really don't understand. They think that centripetal forces go in this list. When they're studying circular motion, they think the centripetal force is a new type of force, like weight or normal force or friction. Notice there were no new forces here. We're just using the same old forces we were already going over: weight, normal force, and friction. There were centripetal forces, but those are just the same old forces in a particular direction. Who's the centripetal forces here?
Weight and newtons.
What the N stand for?
Normal.
Weight and the normal force. Although we might call the weight an anti-centripetal force here. But yeah, and what's the centripetal force here?
Normal force.
Not the weight. All right, but notice it's still the normal force. So for example, I just want to warn you of a mistake I see people make a lot of the time. I might say, I'm asking you what are the forces on the object. So a lot of people say, well, one of the forces on this object is the centripetal force. Well, that's completely meaningless. We need to identify the types of forces. It's just like, suppose I asked you what are the forces on this object, and you said, oh, there's an X force. Well, that doesn't do us any good. We need to name the actual types of forces on the object, not just the direction. Okay, so it never does you any good to say, oh, there's a centripetal force on the object. Even though there is, you have to say what type of force the centripetal force is.
Normal and centripetal direction.
That's right. In this case, there was a normal force in the centripetal direction. That's a very good way to phrase it. And in this case, there was a normal force in the centripetal direction and a weight force in the anti-centripetal direction. Okay. All right, so hopefully that can clarify. So the reason I try to avoid centripetal is for some reason, people have a tendency to think that centripetal forces are a type of force. I think they're a little less likely. Radial sounds more like a direction. So we're more likely to remember that radial is just like X and Y. It's not like one of these. Okay. So I'm going to stick to radial and tangential, but you should know if you see your instructor say centripetal, that they mean the same kind of thing. Okay. So for example, this equation is usually written in your textbook like this. Centripetal acceleration. Centripetal acceleration is v squared over r. But that's the same as radial acceleration. Okay. Okay, good. All right, so now let's do point C. Same analysis. So this one I want you to try to do more on your own. So try to apply the same exact analysis we've already been applying to point C for the same object. Well, I guess I need a little more information. So forget about physics. Remember at this point we were moving at 15 meters per second. By the time we get to here, would common sense tell you we're moving faster or slower than 15 meters per second?
Faster.
What's your answer?
Faster.
Forget about physics, use common sense. Think about an actual object sliding around. Would your common sense tell you it would be going faster or slower here?
Slowing down.
It slows down and then it starts speeding faster.
So at this point would be going faster or slower than D.
Slower.
Right, which I don't think was your first answer.
Yeah.
Yeah, right. But as something moves up the track, gravity is going to slow it down, right? And if there's friction, that'll slow it down even more. Things don't speed up as they move up a track. Okay. So I'll just make up a number and say that here, let's say that here the speed is 12 meters per second. All right, now let's figure out everything we can about that point. So we have to, did you write down your axes?
Yeah.
Good, we already had those down before. You made a free body diagram. What's one of the forces on this object?
Weight going down.
How do we know the weight is down? Because the weight is always down. What's another force on the object?
Normal force going up, away from the surface.
How do you figure out the direction of the normal force?
It's going away from the surface.
What direction would be away from the surface here? How do you know?
Because it's pointing away from the surface, so it's pointing up. And the weight's going down.
Where is the box?
At the top.
At the top, so,
Here?
yeah.
Yeah.
Now remember, actually try to visualize the movement of this box. Is the box sliding around the inside or the outside of the track? Right. It would. It's impossible for this box to slide around the outside unless it's connected, right? Unless it was actually like on railings. But you can see from the picture that the box is on the inside of the track. So what's the direction of the normal force?
Same,
Same direction as the weight going down.
Up or down?
down.
That's right, because if the box is here, then the normal force has to push away from its surface towards the object. Maybe that's a better way to put it. The normal force always points away from the surface towards the object. The normal force always points away from the surface towards the object. I mean, you know that from common sense. So, for example, will the normal force prevent me from pushing this eraser down?
Yes.
Will the normal force prevent me from pulling the eraser up? No, piece of cake, right? Normal force can only push up here. It can't pull down. Will the normal force prevent me from pushing the eraser into the whiteboard?
Yes.
Yes. Will the normal force prevent me from pulling the eraser away from the whiteboard?
No.
No, unless there's glue, the normal force can only push away from the surface. It can't pull in to the surface. Ah, rats. All right. All right, so is the normal force going to prevent me from pushing the eraser up through the ceiling?
Yes.
Yes. Will it prevent me from pulling it away from the ceiling?
No.
No. So notice the normal force does not pull up at this point. It can only push away from the surface unless there's something like glue or something. Okay. Okay, so that's one of the crucial steps here. That's why it's not just, notice that this is time consuming. It's not enough to analyze A and D. C is different. Each of these points is a different analysis. Okay, so go back and incorporate that into your logic and try to continue with the problem.
I got 20.
this be plus 490 or minus 490?
Isn't it 49?
Did I make a mistake?
No.
5.
Oh, thank you. My
Yeah,
mistake.
me too.
That's right. Plus 49 or minus 49.
Plus 49.
Right, but the way we were attacking the problem originally, this would have been a minus, and you can see you would get the totally wrong answer at this point. So getting the directions right is crucial. For some reason, it's hard for students to recognize how important directions are, but the directions give you the signs. Is there a big difference between someone giving you $1 million and paying someone $1 million? Yeah, well that's a sign or a direction. Notice the direction is more important than the magnitude. It's more important to know whether someone's paying you or you're paying them. That's more important than the amount of money, right? The sign is more important than the number. The sign, you know, if I was the grader, I would give someone who got the sign right more points than someone who got the number right. The sign is more important. It's more important to know whether you're getting money than, or receiving than how much the money is. Is there a difference between going 5 miles north and 5 miles south?
Yeah.
Yeah, it's more important to know what direction you're moving than how far you're going in many cases. The sign is more important than the number, but it's hard for people to kind of recognize that. Okay, so. What did you get as your answer?
It's weird. Positive.
Positive 23 units.
Is the normal force. Okay, very good. Great. So that's how we would go through with this. So notice all of these points were different. What was making this object move in a circle? What force?
Normal force.
Anything else?
The ratio.
Was the weight? Now notice, remember, we don't.
Right.
It doesn't help us call it the radial force. We have to focus on the types of forces. So is the weight here helping us to move in a circle or keeping us?
Helping.
It's helping us. That's why the normal force is lower than ever now. If you compare this answer to the two previous answers, here the normal force has a really easy job because the weight is helping it, and we're going slower than before. Here, the normal force had to be bigger than at point C because it's not getting any help from the weight, and we're going faster. And here's where the normal force had to be the greatest because we were going the fastest, and here the weight was fighting against the normal force. Notice the big difference between A and C. Here the weight fights against the normal force, and here they're cooperating to help each other. Okay. Very good. Would you agree that if the weight increased, the normal force could decrease at point C?
Yes.
If this increased, the normal force would decrease because the weight would be doing more of the job. The greater the weight becomes here, the smaller the normal force would be. In fact, if the weight was big enough, we wouldn't need any normal force at all.
That makes sense. 'Cause at the bottom, you need the most normal force because the weight is
Pulling against you. All right, you always are going to need a normal force down here. So, would you also agree if we go faster, we would need more normal force at point C?
Yes.
You can see that from the equation. The faster we're going, the more normal force. All right, because remember that an object in motion tends to continue moving in a straight line. The object wants to keep moving like this. What is it that's forcing it to stay on the circular path? Well, the weight and the normal force here. The faster we're going, the greater the normal force has to be. What if you slow down? Then you don't need as much normal force. Now, if you think about it, if we were going too slow, we would lose contact with the track, and we would not actually be able to move around in a circle, right? If we were going too slow, your common sense should tell you that you would lose contact with the track, and you could not actually move in this circle. You don't need to worry about going too fast, right? The faster you go, the greater the normal force increases. The normal force can just keep getting bigger and bigger. I guess theoretically you might be going so super fast that you burst through the track, but we wouldn't see a problem like that in this course. But you could be going too slow to stay on the track. So that's a common type of problem. A common type of problem is how slow could we go at point C and still stay on the track? So let's talk about this together. Now notice we're not going to use this number anymore. Now we have to ask for a slower speed. So what's the framework we're going to use to work that out? Well, still Newton's second law. And we know that generally we only need the radial component for circular motion. What do we plug in on the left-hand side?
49 units. Positive. Plus n dot. Plus 0 equals 5 kilograms.
And what was the question asking us for?
Velocity.
Yeah, I didn't quite write this out right. And our R here is 10. So the question here is asking us for V. So it looks like we have a problem because we have one equation and two unknowns. You might think that you would use now the tangential equation, but remember we're almost never going to need that in this course. Well, here's the thing. What we need to do is we need to imagine the situation where we're just barely maintaining contact with the track, right? That's what they're really asking. At what speed would the object just barely be staying on the track, right? Well, what does the normal force tell you? The normal force tells you how hard the object and the track are pushing against each other, right? The normal force tells you how hard the object and the track are pushing against each other. If the object is pushing really hard against the track, would the normal force be big or small?
Pushing hard against the track.
Maybe I didn't phrase that right. If the object is pushing really hard against the track, would the normal force be big or small?
Big.
That's Newton's third law. If the object is pushing hard against the track is pushing hard against the object, which is the normal force. If the object is pushing only loosely against the track, would the normal force be big or small?
Small.
If the object is just barely maintaining contact with the track and is about to leave the track, what would the normal force be? 0. That's the key to this problem. If you're just on the verge of losing contact with the track, then you're just barely pressing on the track at all. And at that point, the normal force would be 0. That's the key for solving this question. Notice that this is a whole different question than the one we did before for point C. Because here we had a different speed, and the normal force was not assumed to be 0. So this is the key for doing these problems that ask you how slow can you move around the circle and still maintain contact. This is a pretty popular type of question. The key is, well, if you're just barely on the verge of staying on the track, if you're just about to lose contact, the normal force would actually be 0. And then what do we do?
Solve for B.
So let's go ahead and do that. Okay. So this is a harder type of question that students often don't know how to deal with. So when we're asking how slow can we move and still maintain, stay on the track, we need to think about the situation where we're just barely maintaining contact. The hidden we've seen how many times that we've had hidden zeros that are crucial. Here the hidden 0 is that in this case the normal force is 0. Now remember, that doesn't mean the normal force is always 0. It was just for this particular question that we had to put in a normal force of 0. Notice how this is a slower speed than we had here, because here there really was a normal force. Okay? So if we're moving at 9.9 meters per second, what is going to keep us moving in a circle?
The weight.
Just the weight. Because we're moving so slow, the weight can do the job on its own. Because we're moving so slow, the weight can do its job on its own. Let's say we started moving at 11 meters per second. Then the weight wouldn't be strong enough. So what would keep us moving in the circle there? Then there would be more of a normal force. Let's say we upped the speed to 20 meters per second. What would happen?
Normal force.
Would have to increase, because the weight can't change. The weight can't respond. it's always mg. It's the normal force that's going to respond, and you know this from common sense. The faster you'd be moving, the more the object would be pressing against the track. Right? That's why I said that if you were really moving at supersonic speeds, it might actually break the track and press through, even though you wouldn't see a question like that in this class. Okay, so hopefully we now have a little bit of understanding of that type of how things are, what happens when you change your speed. It's the normal force that changes to respond to that. Okay, this would be a good question to try again. This is pretty popular on exams.
Can you show us a point where n would not be 0, or is it just, would it, because you said at that particular point it's n is 0.
If you're going at the slowest possible speed to still stay on the track, right? Remember, if you wanted an example where n was not 0, we'd already done that earlier when we said we were going at 12 meters per second, right? And then n was 23. And we'd also found non-zero n's at these points as well. Okay, so, but even at point C, n doesn't have to be 0 unless you're going at the slowest possible speed. So what was the slowest speed that you could go past point C and still stay on the track?
9.8.
9.8. So what would have happened if the object was going at 5 meters per second at that point? It would fall off. It wouldn't fall straight down, because inertia would still take it to the right. But if this is the track, it would go like this. Okay. And once it's lost contact with the track, it's never going to get back, because you can never feel a normal force again once you've lost contact with the track. Okay. This is a kind of different type of question. Any idea what we could figure out about this situation? Doesn't even have to be a track.
Velocity can be the same throughout the track, right?
The magnitude of the velocity will be the same everywhere. Not the direction, clearly. Okay, that's right. Anything more concrete? We can figure out how long it will take to move in one complete circle. We could figure out how long it would take to move in one complete circle here. Any idea about how we should start working on that?
Isn't the equation 2 pi r over t?
Okay, good. Let's not go straight to that equation though. Let's see where that comes from. So what's the first thing? Forget, instead of using that memorized equation, logically, what do we have to figure out first here to figure out how long it'll take us to move around the track?
Acceleration.
Take your time. Well, the first thing we need to know is how long the circle is. What's the name for that?
Displacement?
In geometry?
Circumference?
Circumference. We need to know the circumference of the circle. You guys remember this formula for that?
I do not.
Any idea?
Is it 2 pi r?
2 pi r. That's right. So let's work that out. What are the units on that?
Meters?
All right, I'll round that to 50.3 meters. Okay, good. Now how can we figure out how much time it'll take us to move around that track? Well, this is like a kinematics problem. Should we use the a equals 0 or a doesn't equal 0 approach?
Equals 0.
Because we're moving at constant speed. Because we're moving at constant speed. This is a little bit tricky because we know the radial acceleration is not 0. The radial acceleration is not 0. But remember, the radial acceleration doesn't affect your speed, it affects your direction. If we're moving at constant speed, the tangential acceleration would be 0. We only talked about that briefly. But the tangential, remember the tangential acceleration affects your speed, the radial acceleration affects your direction. So if we can moving at constant speed, there's no tangential acceleration. So what would be our framework for solving this?
Kinematics, that would be...
So how would we attack that?
We would write the units that we have? Yeah.
So did we decide this is a problem that's where it's similar to a equals 0 or a is not 0?
A equals 0.
Because the speed is constant. So how do we attack that type of kinematics problem?
Should write down all the variables we have?
Actually, we don't need that for this situation.
Oh, okay.
Velocity times time, isn't,
So we need a complete equation.
yeah, so delta x is equal to velocity times time.
Right, do you remember there's only one equation that we need for this version of kinematics? Now in this case, it actually, since we're not moving along any axis and we're moving in a circle, it makes sense to call this distance. Remember, this should be an easy equation to remember. This is just the high school equation, distance equals speed times time. If your speed is constant, then your distance is just your speed times the time. The reason we can use this is because we're moving at constant speed. Since we're moving at constant speed, we can use this equation. What's the question asking us for?
Distance.
I guess I didn't quite give you a question, but what can we figure out? Well, what can we plug into this equation?
Plug in the velocity.
What's that?
5 meters.
Anything else we can plug in?
Distance is 50.3
50.3 meters.
That's the reason we figured out the circumference here. This is the distance.
So 10.
All right, I'll round that to 10 seconds. How do you interpret this number? 10 seconds to do what?
To complete the whole.
Complete the circle.
10 seconds for one circle. So suppose the question asked you, how long would it take to do 2 circles?
26.
So, yeah,
How long would it take you to do half a circle?
5 seconds.
All right, so you would still solve it the same way. First you figure out how long it takes, whatever they're asking, first you figure out how long it takes to do 1 circle, and then you can adjust that. Okay, so ideally we would do a bunch of practice problems with this, but we're short on time, so I've just showed you one problem. But just as usual, this won't do you any good unless you can practice this again on your own and get used to attacking this and hopefully find similar problems that you can work on. Okay, so this obviously, this is almost more of a math problem than a physics problem. But this is something else that oftentimes comes up on circular motion. Notice we don't need Newton's second law for this, we just need a very simple form of kinematics, distance equals vt. By the way, if you solve this for t, what do you get?
You get distance over velocity.
And how are we calculating the distance?
We calculate by circumference.
And what's the formula for that?
IR.
This, I think, is the formula that you had mentioned earlier. There's some formulas that we have to memorize in physics, but we shouldn't have to memorize this formula. This process should make good sense to us. This is the distance and this is the speed, so that's how we're figuring out the time for this type of problem. Okay.
What were you saying was that I missed something where you said that it's good with constant speed, but it's different than the radial speed because it's
Yeah.
moving?
So,
Can you repeat that?
yeah, that's something we just don't have time to go over that very clearly, but the point is, what does the acceleration change? Remember that in ordinary English, your acceleration affects your speed.
Direction.
But in physics, your acceleration can affect your speed or your direction. The radial acceleration affects your direction. The radial acceleration changes your direction. The tangential acceleration changes your speed. That's what I was trying to
I
say.
said around the circle.
The radial acceleration affects your direction. The tangential acceleration affects your speed. So which is 0 here? The tangential acceleration or the radial acceleration?
Constant. Sorry, it's the tangential.
Because it's the speed that's constant. So which acceleration is 0? We know the radial isn't 0 because it's given by this formula, v squared over r. I wanted to mention that because remember we were saying that a equals 0 for our kinematics. Well, it's the tangential acceleration is 0. The radial acceleration could never be 0 for circular motion. Okay.
Direction.
So let's look at this. Something else that oftentimes comes up here is you have to recognize that there's two types of circles. There are vertical circles and horizontal circles. The example that we did with the track, is this a horizontal or vertical circle? Vertical. What would a situation with a horizontal circle be like? So imagine, say, a tether ball. Let's say you hit the tether ball. It would move around the pole, right? Would that move around? So let's say I hit it straight like this. Then it would move in a horizontal circle, right? So let's do an example about that. So this is a tether ball setup. Here's the rope, here's the tether ball, here's the metal pole. Now, would you agree it's hard to draw a horizontal circle?
Yeah.
Because the circle is coming out of the board and into the board. Technically, it's impossible for me to draw the circle that this is moving in. But can you visualize the circle that is going like this? It's coming out of the board, then going here, and then going behind the wall and coming back over here. Maybe we could draw it like this. But you have to remember, this is not the same type of circle as before. This portion of the circle is in front of the whiteboard, we have to imagine. And I'm using a dashed line for the portion of the circle that's behind the whiteboard. So it's not, this point is not higher than this point. This point is behind the board, and this point is in front of the board. So it's a little bit tricky to draw horizontal circles. So let's talk about this together. Okay, what framework would we use here?
The Newton's second law.
That's what we pretty much always use for circular motion, although we saw sometimes we have to use some simple kinematics for Newton's, for circular motion as well. So one thing we have to do is draw our axes. So try drawing the axes here. What will be the direction of the radial axis?
Center, so left.
That's the key. Now, remember that there's two other axes. One is called tangential and one has no name. Is this the tangential axis or the no name axis? This is the no name axis. Where's the tangential axis?
Going down. No.
That would just be the anti-direction to this. Where's the third axis?
Oh, horizontal, like coming out at us?
Yeah, it's in the third dimension, right? Coming in and out of the board. There's another axis here. Do you agree this would really be tangent to the circle? If you can imagine a tangent, this is not tangent to the circle.
That's correct.
Because this is a horizontal circle. If it were really going to be tangent, we'd be coming into and out of the board. Okay, so the tangential axis here is the one that's going into and out of the board. The vertical axis is the no-name axis. Okay, this is why I had to mention that no-name axis. So in a problem like this, I'll just call this the y-axis. Okay, I'm not going to bother drawing the tangential axis because in your class, the tangential axis usually won't be important for horizontal circles. Okay, so now let's continue with this. So You both got the radial axis correct, which is what's most important, but I think you both thought this was tangential. When it's really no name, so we can just call it the y-axis. Okay, now what's the next step?
It's the free body diagram.
Free body diagram. What's one of the forces on this object?
Wait.
What direction is that?
Going straight down.
Good. Are there any other forces on the object?
Tension.
That's right. How do you know? You ask what's touching the object. So what direction is the tension in? North, west, or southeast?
Northwest.
Because that's the only way a rope can pull. A rope can't push, it can only pull. So the rope must be in this direction. Good. So that's any other forces?
That's it.
Because there's nothing else that's touching it. Now, I had mentioned hitting the object. Well, if I hit it, I would be exerting a force on it. But I'm not thinking about hitting it anymore. Now I'm thinking about how it moves after it's been hit. So after it's been hit, nothing is touching it except the rope. Okay, good. So we need to make our force table. So what can we write down about the weight?
W is mg, W equals 6 and 9.8, which is
So what's the radial component and the y component?
the radial component is 0, and the y component is negative 9.8 newtons.
Isn't,
58.8, what am I doing? Sorry.
Negative.
Yeah.
Now let's try the tension. What can we write down about that?
Tension, the magnitude of tension, and then tension in x direction. We gotta break up the components.
yeah, isn't, Tx is equal to tangent times cosine 20? Oh, sorry,
Sine.
sine 20. And then-
I shouldn't say x. We got t radial and ty.
So Ty would be T cosine 20.
Times t, right. Ty is cosine 20.
Did you draw a right triangle?
Yes.
Times t.
How do I label this side?
That is the rope. So that's tension.
T.
How do I label this side?
That's
Ty.
T cosine
Oh,
20. So Ty.
tx.
Good.
TR.
So tr would be better down here. So tr really is using the sign. That's right, because it's opposite to the 20. And ty really is adjacent to the 20. Good, but we should have done the signs here first, which is positive or negative.
Tr is positive. Ty is also positive.
Because these directions are up and to the left. By the way, remember how I told you that you should always make the radial direction towards the center? Well, this is why, to get as many positives as possible. The reason why these are all coming out positive is because we chose the radial direction towards the center of the circle. If you don't do that, you'll get more things that should be negative, and students are not good with negatives, so it's better to keep things positive. Okay, good. So I'll let people have trouble with this because they get nervous when they can't get an exact number for this. But we don't have numbers, we have expressions. What can we do now?
Now we can use the f of r and the r equation.
What would we plug in here?
We would have 0
Plus.
plus sine, positive sine of 20 t equals 6 times
V squared over R.
v squared over r. There you go.
Then what?
We don't know velocity, right?
Right.
So,
Oh, I didn't give you enough information. So I should have said that we're moving in a circle that has a radius of 3 meters. I should have added that information. So now what?
V squared over 2 unknowns. And then we plug it back in.
So now what?
Isn't T unknown?
It is an unknown, yeah.
So we can't solve it, and then.
Okay, so as you've seen, we have a problem,
Yes,
because we still have 2 unknowns.
right.
Anything we could do now then?
Yeah.
Or are we, or to continue making progress?
F, maybe try FY?
Yeah, I told you earlier that on these problems you usually only need the radial axis. But I can see now that was not quite true. This is a problem where we need the y-axis as well. So what's the left-hand side of this equation?
Negative 58.8 newtons plus cosine of 20 times t equals
Isn't it equal to 0?
6 times ny.
So can we plug in v squared over r for a?
No,
Why not?
because it's not a radial direction.
That's right, that was a trap, good. We can't plug in v squared over r because this is not radial. So what could we put on the right-hand side?
0.
0.
0. How do we know ay is 0?
It's moving in a radial direction, it's not moving in the y direction.
It's moving horizontally but not vertically. Yes. This is going to be moving, so there's no y movement. So as we saw on our earlier problems, if there's no movement along an axis, the acceleration there is 0. Notice how crucial it is not to confuse a y and a radial at this point.
Okay, so t.
What'd you get?
63.2 newtons.
I got 62.6.
There's my calculation.
Okay, you just rounded differently. What was your answer again?
62.6.
Okay, yeah, so depending on how we round, it might be like 62.6 and the units are,
Newtons.
okay. Then what?
And that plugs back into the f of x.
Good. Maybe it's more organized to plug it into our table first.
Okay.
So we now know, we can now work out these two things.
What did you get? 20, 62.6. Sine of 20.
Yeah.
So what did you get?
3.2 meters per second.
Okay, I would round that to 3.3 meters per second. Okay. This is the first problem that actually might be hard enough to be on the test, unfortunately. It takes a while to get to the high level difficulty problems. So this could be a real test problem. This is a high enough difficulty for a real test. Most students have no clue how to do this, but you can see it's just an application of the types of methods that we've been using so far. All right, so we spent most of our time on vertical circles, but horizontal circles are fairly common on the exams as well, so I wanted to see an example of that. And I can see that I misspoke earlier. I was saying that on circular motion in this course, you only ever needed the radial component, but I can see that's not right. There are some cases where you will need another component. Notice this is not the tangential component, it's just a no-name component, but we still needed it in order to solve the whole problem. So in this case, we needed both of those two components. Okay, all right, well again, it would be important to go back. We did a bunch of questions together, but we only had time to do like one example of each thing. So it's really important to go back and try to redo each of these problems on your own. And as we saw, that doesn't mean looking at your notes, it means looking at the problem, covering up the answer, doing the whole thing on paper, over and over until it's easy to get through that problem. And then, hopefully, taking that time and doing more of the circular motion problems you were assigned in your homework. But I would say it's futile to attempt the homework problems until you can get these problems from the tutoring session right easily. Like I said, most of these problems were probably a little bit easier than you would see in the homework or on the test. But it's futile to jump into the deep end of the pool until you understand the basic techniques. Hopefully now we've gone through enough of the basic techniques that now you have at least some techniques that you can use to apply to some of the harder problems in the homework. But again, first make sure you can get these problems right, and then you can try the homework type problems. Okay, good. So I was going to say, sometimes when I ask people what the frameworks in the course are, sometimes people say one of the frameworks is circular motion. But maybe you can see now why I wouldn't agree with that. Circular motion is not a new type of problem. It's just an application of Newton's second law. It's just an application of Newton's second law, which is why we had to do Newton's second law first. We're still making the free body diagram. We're still making the force table. The only thing that's different is we have some new names for our axes. New names for the axes: radial, tangential, and no name. And we have this one new formula that we can plug in for the radial or the centripetal acceleration. Other than that, they should be pretty similar to a lot of the Newton's second law problems that we did before. Remember, I've been using the term radial, but your textbook might use the term centripetal. We've been using this equation. You might have seen a different equation, though, in your textbook. You might have seen, or in your lecture, you might have seen this equation. Yeah. Instead of centripetal acceleration, centripetal force. So I just wanted to say, notice we didn't need this equation. So I would encourage you, don't use this equation. It just confuses people. Don't use this equation, it just confuses people. Use this equation instead and plug it into Newton's second law. But hopefully now you can see where your textbook is getting this equation. If you write down the sum of the centripetal forces equals m times a radial. And what can we plug in for a radial?
B squared.
B squared, or you multiply by m.
And notice how now, this is where it's coming from. But I think it's very misleading to students to present this like it's a brand new equation that's completely unconnected with the course. This is just what we get when we plug this formula for centripetal acceleration into here. The other reason why this is quite poor is it leaves out the summation sign. It makes it seem like centripetal force is a type of force. It makes it seem like centripetal force is a type of force with like a new equation. It makes it seem like just like weight is mg, centripetal force is mv squared over r. But that is not a correct analogy. So this is not a new type of force. Centripetal just is a direction for forces. So I just want to mention it's better to avoid using this equation. Instead, I recommend just doing the problems the way we've been doing them, by plugging into Newton's second law. And then when it's appropriate, you'll get something that looks like this, but you'll understand where it's coming from. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.